Okay, here we go again. So here we have a water film, and they do break. They're kind of hard to break, but can break them. Here I've got some tracer particles, a water solution of tracer particles, and you put a drop or two of these fades onto the film, and you can watch what happens in terms of fluid flow within the film, which is going on all the time, but you just don't know it because there's no way to make a visual. And by blowing on the film, you can induce rotation within the plane of the film, and you can see the streamlines left in the wake of the fluid motion as outlined by the tracer particles. Definitely nice, well-behaved laminar flow. And these films being around 300 microns thick, they're a lot thicker than a soap film. I don't think that soap films can exhibit this kind of behavior because they're so thin, of the order of a few wavelengths of light thick, is why you get those interference colors. And these films being 300 microns thick don't exhibit those colors for one, plus it will allow these kinds of fluid flow motions to occur. Another thing we found with these kinds of films is that bubbles are excluded, almost always excluded in the process of drawing the film. And if you do happen to have a bubble in the film, it will soon pop and be expelled from the film through the process of popping. It's as if the bubble, the thin surface of the bubble that is exposed to the top side of the film, it's sucked thinner and thinner until it pops. And here's another tracer drop being put on a film. And by virtue of putting a big drop onto the film like that, it induces its own series of flows. And you can see the little swirls induced from the drop impacting into the film. And here's some red food coloring that was left over from frosting our Christmas cake. And it makes an interesting tracer material as well, although it has a small amount of alcohol in with the food coloring. So now you've introduced another liquid constituent. So you've got some liquid diffusion as well as the pigment from the food coloring. And here's a film where I've added a number of drops of the particles. Here's the film after you've stirred it all up, got the particles in there, and then you end up popping it. Now here we've got a sphere of water, and this is about a 2.5-inch diameter sphere of water, and we've lassoed it with one of our hoops. And it's just happy hanging on to that hoop. So now we've got a nice controlled sphere which makes a pretty decent lens. And what we're going to do now is we're going to draw off as much of the water as we can with a towel and leave a thin film in its place. So you can make these films by just sticking a hoop in a 2D baggie, in a two-dimensional beaker like a Ziploc bag, or you can start off with a sphere of water and slowly suck off all the water and just leave a thin film in its place. And at this particular stage, you end up having something that looks like a cross-section of a lens. It actually works as a fairly decent lens. I guess you could call this a meniscus lens. Here's the final stages of forming a film. That film is probably about 1 millimeter thick. And we'll do one more draw and and we'll end up with a film that's about half the thickness of the wire. At least that's what it looks like with your eyeball. And now we're going to put more food coloring on it. Since we had some different colors, we decided to see what happened if we put in several different colors of food coloring onto this film. And what you have now is sort of a diffusion experiment where if you don't stir the film up, you just slowly see the effects of diffusion in 2 dimensions as the food coloring diffuses out into the rest of the film. And now we're blowing on it with a tip of a cannula and a syringe, and you can see how just the slightest amount of force from the air will make the water move, and if the water has pigment in it, why then the pigment will move, as you're seeing there. Because diffusion is a rather slow process, these patterns will stay present for up to an hour or more. The edges will start to get fuzzy as time goes on, but the basic patterns will stay there. And here we have, we thought this made a nice little eagle-looking, so a little eagle-looking pattern, and so we've been able to make thin film art using our food coloring, water, and a little bit of stainless steel safety wire. And this is Sox is doing the work with the cannula there, blowing the food coloring around. And this pattern lasted for about an hour. We were able to watch this. It makes us wonder what someone like Batiste could do with a medium like this. And here we are in our little laboratory. It's actually, we turned the shower into our little wet water laboratory here. And just another view to show that the film genuinely is a thin film. And there it is after about 20 minutes. You can see the edges start to get diffuse from diffusion. They start to get fuzzy. And now I'm going to speed this up a little bit while Sox continues to finger paint with the little wisps of air. The resultant viscosity of the water is such that if you gently blow it around, the patterns will stay there. Unless you stick the cannula into the film and stir it up, get in induced motions, it'll just be happy to sit there and let diffusion take its place. It's like reducing the degrees of freedom by 1 so that you have a 2-dimensional problem instead of 3-dimensional problem dramatically reduces the effect of any kind of possible convection and fluid flow. And here we put a bubble on the surface to show what happens to bubbles, and it's like this bubble is thicker than the film, and so the part of the bubble that sticks above and below the film is thinning, and it's like the capillary forces keep thinning that, and it just makes these bubbles want to pop. So it's a way to kind of get rid of bubbles. If you don't want bubbles in your system and you run them across a film like this, it's like the film will want to make the bubbles go away. And here's what happens after we've stirred all the film up, and we get this kind of yucky green color. And I think this is conclusive proof that here on the space station we've discovered what the true color of the universe is, and this is it.